let's look at a couple simple examples from chapter 1. Probably things you've seen before, but now we want to consider it in terms of where those differential equations come from, and then we'll do kind of expand on it from there. So first idea was the free-falling objects. Again, probably seen that in physics or somewhere in math or calculus before. So what we're talking about then is you have some object of mass. Gotta go faster, I guess. Okay, so you have some object, and I usually use like a cursive M for mass. So we're gonna let M denote, that's the proper way of saying it, mass of an object. And g, the acceleration of gravity. The acceleration of gravity. Then we think of this as, like a vector kind of thing, like that. And then this would be like the ground. Like down here. Then you have a height, h, that it would be falling. And we use, okay, before I go on, we use the concept of Newton's second law. So Newton's second law says force is equal to mass times acceleration. So you can picture you have like you're pushing something. You have to accelerate it. You have to go from a position of maybe you got a car rolling just a little bit, and some of us have pushed them. They're really heavy. But once you get it going, there's a force pushing it. So how much force you push has to do with the mass. And then the acceleration is, it has to speed up somehow. It's not a constant speed. It's speeding up or slowing down. So then we say force is equal to mass times acceleration. F equals ma. We've probably all seen that. And so we consider this a negative force, mass times acceleration, down. Think of h as a position function or of the object. So think of h as a position. We would use like s or something maybe in Calc 3. Position function of the object. So when it's just sitting there, the forces are balanced. So the forces are balanced. So we say like F1 equals F2. And so okay, so then what we have is the mass times, so this is acceleration due to gravity, and then you have a mass times its height. So the forces have to equal. So the mass is going to be constant, whatever that is, but your h is being accelerated. So it's h double prime of t must equal negative m times g. Or you could write that as the second derivative of h with respect to time, where you write mass and then be d2h over dt squared is equal to negative mg. So this is the differential equation. That's how you would get the differential equation, or a differential equation, out of this whole thing. This is, of course, ignoring air resistance and all that. That will add in later as we go. So you can see, of course, the masses will cancel on both sides, which I'm sure you already know that. Doesn't matter the mass, the acceleration of gravity is the same. So you end up with d2h over dt squared is equal to negative g. And then that's easy to solve. So you integrate both sides, you get dh dt equal to negative gt plus c1. Integrate again, and you get h of t equal to, I already ran out of room again. Sorry for the nuance there. You know, I realize is you can speed these videos up and it goes much faster. Obviously, if you're copying down, you probably want to go at this speed, but if you're kind of reviewing, go like double speed. Well, not quite double speed, but anyway, negative a half g t squared plus c1t plus c2 is what you get. And that's, of course, no air resistance. And we've gotten into other things with that. I mean, you know that you do h prime and you get velocity, and then you double primes the acceleration. But this is one way how you derive it. Okay, let's do another one. This is radioactive decay. So we will, to digress, I'm sorry, we will expand on this and throw in air resistance and kind of keep this one going. Probably that in radioactive decay, kind of keep that going as well. I'm not going to focus on, there's all kinds of things we can focus on. So I need to just pick a couple that you're probably familiar with and show you how solving those differential equations has to do with the techniques we're learning. Okay, then let's look at radioactive decay. Another, one we see all the time. So a couple assumptions for radioactive decay that's been highly tested, of course, is this. So the rate of decay of a substance, right, is proportional to the initial amount of the substance. Okay, so, sorry about that. So that's something, I guess you could think of it as intuitive, but it's been tested. I mean, this is something that's been scientifically tested over and over and over. So tested, I'll just say, it's a tested assumption. So it's used scientific method to test some of these hypothesis stuff and see how it matches up in the math. And of course, it's true. And there could be other nuances in there when you put in more variables, but that's the fundamental simplified version of everything. So when you set this one up, we're going to let A denote the initial amount. Denote the initial amount of substance. So, and we make the assumption A is greater than 0. T is time. Right? T denotes time, etc. K is the proportionality constant, depending on the substance. So that could change depending on what it is, but we'll just say it's proportional, so we keep that. So therefore, what you get then, almost forgot, this was separable, right? This is already separated. I mean, you basically just integrate. You could bring over the dt, and you're just integrating. So this is pretty straightforward. Same with this one will be as well. That was toward the whole point of doing this one. Okay, so therefore we have the rate of decay. So the rate is dA dt. So it's changing. And if it's decay, it's getting smaller. So it's negative k times the amount. And in this case, we're assuming the k is positive as well. Okay, so now solve. And that's, of course, the separable equation. Separable differential equation. So you get 1 over a dA equal to negative k dt. And let me show you some logic here. I'm deliberately putting in an implication, not an if and only if, because you have a constant factor of integration. So you can't go back without knowing that constant. So deliberately putting in an implication symbol and not an if and only if symbol, just FYI. Try to go over some of this logic stuff with you as we go. Integral of 1 over a dA is equal to the integral of negative k dt. So we integrate that. And that is just natural log of absolute value of a, but a is positive, so we'll ignore it. Plus C1 equal to negative kt plus C2. But these are both just constants, so we just need one C. So we would rewrite that as ln A equal to negative kt plus C. Right, where C technically is C2 minus C1, all both constants, so we don't really care. Okay, now solve for A. And by doing that, you raise it to E, right? So you get all of this. Just go ahead and recopy this. Make it look nice. So this is that could be an if and only if, but I'll just say implies right now. So that's, you raise e to both sides, so you have a equal to e to the negative kt plus c. Okay, and then that's definitely an if and only if. A, if and only if, equal to e to the negative kt, and that's just e to the c, which is, of course, just a constant. So this is an arbitrary constant in of itself, and so we just can write it as we'll put a capital C. How about that? So we'll say this is equal to capital C e to the negative k t, where c is e to the c. Okay, so again, that's a differential equation that comes out of an application, and you need to be able to solve it. And then later, we'll talk about the initial conditions, or we already have, I don't know, where you can find those constants. You can look for those constant values. And then usually the k depend on the substance in question. Okay. So the solution of the differential equation is a function, like is another equation. So that's one thing we're keeping in mind, is the solution to a differential equation is an equation, or if it's explicit, a function, or it could be like an explicit or implicit function, but that's what you get for the solution. So just be a little careful with that concept. Okay, so that's all I had for applications, and there's all kinds of stuff you can do, but we'll do a little bit as we go.